The universe may have no beginning, a bold idea that rewrites how we think about time, cause, and our own origins. Across physics, from quantum gravity to cosmology, researchers chase models where time stretches back without a first moment. In this video, we'll unpack what a cosmos without a starting point would look like, how such ideas might be tested, and what counts as evidence when there may be no edge to observe. We'll separate the myths from the math, explain the core ideas in plain terms, and show why this question matters to anyone who has ever looked up at the night sky. Stay with us as we trace the logic, face surprising implications, and imagine a universe that keeps going back without a starting pistol. Concept of a timeless universe. In physics, time is intertwined with space in the fabric of space-time, described by relativity. Some approaches, however, treat time as not being fundamental. A timeless universe idea posits that at the deepest level there is no external clock, only relations between physical degrees of freedom. The mathematics of this viewpoint often uses a wave function without an explicit time parameter. The Hartle-Hawking no-boundary proposal offers a geometric picture where the universe has no initial boundary in time, smoothing what would be a singular beginning. In canonical quantum gravity, the Wheeler-DeWitt equation describes a quantum state of the universe that does not evolve with time in the usual sense. This leads to the problem of time. Rather than a ticking clock, predictions come from correlations among variables, such as the reading of one clock being tied to another. Decoherence can produce an emergent arrow of time from entanglement and thermodynamics. The thermal time hypothesis adds another angle, suggesting that time flow may be a property of states rather than a backdrop of events. Cosmologists frame questions about beginnings in terms of conditions and laws rather than a single moment. Signals we measure are correlations across cosmic time. Some inflationary models describe a past eternal multiverse where new regions bud from the old indefinitely. Observational data can constrain these ideas. Ultimately, a timeless universe shifts the burden of explanation from how did it begin to how are the current relations among fields and forces arranged. The concept also has practical implications for how we interpret cosmological history. If time is relational, the focus moves to understanding how different physical sectors couple and constrain one another. Thought experiments about clocks built from different degrees of freedom illustrate how a sequence can emerge only when comparing systems. The no-boundary idea and similar frameworks invite us to imagine a cosmos without a sharp temporal edge, where the story is told by patterns, correlations, and symmetries rather than a finite starting moment. This perspective invites ongoing dialogue between mathematics, philosophy, and observation, keeping the conversation about the nature of time alive. Theories of a beginningless cosmos. A beginningless cosmos treats the universe as having no single starting point in time, with space-time extending beyond any first moment. In this view, there is no edge where time begins, only an endless unfolding of physical processes. One broad family of models is eternal inflation, where regions of space stop inflating and become ordinary universes while the inflationary phase continues elsewhere. This picture naturally leads to a mosaic called the multiverse, a patchwork of bubble universes each with its own history. Mechanisms like false vacuum decay and the slow evolution of a scalar field drive pockets of space apart and create distinct cosmic domains. Some theories explicitly posit no boundary at the origin. The no-boundary proposal, associated with Hartle and Hawking, suggests the geometry of the early universe is finite in extent but has no boundary in imaginary time, so there is no initial edge to the cosmos. In this sense, the universe could be described by a wave function that does not require a starting point. Another line of thought, often called tunneling from nothing, imagines the cosmos emerging through a quantum transition from a state without classical spacetime. Both ideas reside in quantum cosmology, where the focus is on the whole universe rather than on constituents within a fixed background. Emergent universe models offer a different approach, proposing a past eternal, nearly static phase that avoids a singular start and then transitions into expansion. Such a phase can be stabilized by particular forms of matter content or curvature. Cyclic or ekpyrotic models extend that idea further, positing repeated cycles of expansion and contraction connected by brane dynamics or scalar fields. In these scenarios, observers might hope for subtle imprints in the cosmic fabric or recurring gravitational wave backgrounds, though current data do not single out one picture definitively, and many models remain compatible with observations. Quantum gravity-inspired ideas provide concrete mechanisms to bypass a singular bang. Loop quantum cosmology replaces the bang with a bounce driven by quantum geometry, so the universe contracts to a minimum size and then re-expands. Other approaches rooted in string theory or higher-dimensional frameworks yield cyclic, emergent, or bouncing histories as well. A practical challenge is distinguishing a truly endless past from a universe that simply has a very long, finite history or from features built into the theoretical framework itself. Ongoing observations of the cosmic microwave background, large-scale structure, and the gravitational wave background could eventually offer clues, but no definitive evidence has emerged to settle the question. Physical implications for cosmology. Cosmologists study whether the cosmos might extend infinitely back in time, rather than beginning with a singular moment. The possibility of a universe without a true start reshapes how we think about geometry, causal structure, and initial conditions. Loop quantum cosmology replaces the Big Bang singularity with a quantum bounce, so contraction can lead to expansion without a breakdown. Emergent or past-eternal models imagine a phase of quasi-stable behavior before any noticeable expansion begins. The universe without beginning, cosmosy, ni imevshim tochka starta, invites careful consideration of how physics behaves under extreme past limits. The arrow of time is tied to entropy, and a past-eternal cosmos forces us to explain why entropy grows in one temporal direction. In cyclic or bouncing theories, entropy can accumulate from cycle to cycle, challenging the idea of a repeating, identical past. Some proposals aim to reset or dilute entropy during phases of expansion or through conformal rescaling. Conformal cyclic cosmology offers a way to connect successive eons without a literal beginning, by treating extremely large and very small scales as equivalent. Entropy handling remains a key test of any such model. Observational cosmology tests these ideas by looking for footprints in the cosmic microwave background and in the spectrum of primordial gravitational waves. Inflation predicts a nearly scale-invariant spectrum, but bouncing scenarios can leave distinct features. A suppression of power at the largest scales or specific non-Gaussian patterns could hint at a pre-inflationary or bouncing phase. Gravitational wave backgrounds from a bounce might differ in their tilt and amplitude from those produced by inflation. Current measurements constrain many models, but do not yet rule out a past-eternal story. The Borde-Goose-Vilenkin theorem shows that simple inflating spacetimes cannot be extended infinitely into the past. That pushes us toward quantum gravity or new physics to describe a past-eternal cosmos. Loop quantum gravity, string-inspired models, and conformal ideas offer different routes to resolve singularities and define a consistent timing. A complete picture will require a clear measure of probability across potentially infinite histories and a testable set of predictions. Observational tests and signatures. The idea of a universe without a beginning reframes what counts as an observable test, because any past-eternal dynamics must imprint itself on signals accessible to us today. From the edge of the observable sky, we chase hints. The most developed families of models, bounce cosmologies, emergent scenarios, and cyclic universes, predict that traces of a pre-expansion phase could survive as features in the primordial perturbations and the stochastic gravitational wave background. These traces are subtle, and their interpretation depends on separating them from noise and late-time evolution. CMB, large-scale structure, and gravitational waves form the current testing ground. In the cosmic microwave background, several signatures are discussed as potential hallmarks of past-eternal dynamics. One is a suppression of scalar power at the largest scales. Because a pre-bounce or pre-inflationary phase can alter the initial conditions for perturbations, the observed low multipoles may exhibit deviations from the simple, nearly scale-invariant spectrum. The data hint is inconclusive. Non-Gaussianities, if present with distinctive shapes, could point to a non-standard prehistory and help distinguish a bounce from conventional inflation. Future measurements aim to tighten these constraints. B-mode polarization, sourced by primordial gravitational waves, is another avenue where late-time physics can interfere with prehistory signals. Some models predict a modified tensor spectrum rather than the tiny, scale-invariant imprint expected from simple inflation. The presence or absence of a flicker in the tensor-to-scalar ratio across scales, together with a potential cutoff or ring in the spectrum, would help distinguish a past-eternal scenario. Topological tests offer a complementary angle. If the universe has a non-trivial topology on cosmological scales, one could search for circles of identical temperature fluctuations in the CMB or correlated patterns in multiple sky patches, but current limits favor a large or effectively infinite space. No decisive topology detection has emerged yet. A coherent observational program combines CMB polarization missions, galaxy surveys, 21 cm intensity mapping, and gravitational wave detectors. Lightbird and the Simons Observatory will sharpen large-scale polarization. Ground-based and balloon experiments, paired with future space missions, aim to tighten constraints on curvature, non-Gaussianities, and the low L-power spectrum. Space-based interferometers like LISA will probe the stochastic background in complementary frequencies. Pulsar timing arrays and 21 cm experiments will extend sensitivity to the nanohertz and mid to high redshift regimes where some prehistory signatures could cluster, enabling a cross-check against CMB results. Ultimately, consistency across probes will determine whether a lifetime of pre-expansion dynamics left an observable fingerprint or remains a theoretical possibility. Philosophical and epistemic implications. Some cosmological models imagine time without a starting point, suggesting that the universe extends infinitely into the past. In these views, the cosmos exists without a first moment, and the laws of physics hold across all moments of eternity. This idea challenges the common intuition that every event needs a preceding cause. Philosophically, a past infinite cosmos reframes questions about contingency and the source of explanations. It invites us to rethink why there is something rather than nothing in a way that does not rely on a temporal origin. From an epistemic perspective, knowing a past that is, in principle, unbounded is puzzling. We rely on finite observations to infer the properties of the whole, yet the past of the universe may extend beyond any possible observational horizon. Some models try to explain current order without appealing to a beginning by appealing to symmetry, attractors, or phase states. The problem of induction grows sharper when histories stretch without a boundary. Prediction becomes tricky. If histories extend infinitely, assigning probabilities to events requires a careful measure, and simple notions of prior likelihood can fail. Time may be seen as emergent from deeper structures rather than as a pre-existing stage. Causality could be reinterpreted in terms of correlations rather than linear chains. The absence of a first moment shifts the burden of explanation toward global conditions or principles rather than initial facts. Some philosophers find no-beginning models appealing because they promise a more unified account of existence, while others worry they defer the ultimate explanation to something that cannot be tested. The discussion lands at the edge of metaphysics, but it remains tied to how we imagine evidence and justification in science. Empirical science can still probe past eternal proposals through patterns imprinted in cosmic structures. For instance, the way fluctuations are arranged could bear signatures of the underlying ontological frame. Cyclic or emergent histories may leave distinct but subtle fingerprints in the distribution of matter and in gravitational wave backgrounds. Yet the signatures are often model-dependent, and differentiating them from a finite origin scenario remains a challenge. The epistemic payoff is a more flexible framework for understanding explanation, where time's direction and its origin are not the only options. Researchers continue to test these ideas with observations and with the development of sharper theoretical notions about causality and inference. Here's the takeaway from the universe without beginning. Time may not hinge on a single first moment. The cosmos could be eternal, or its cycles and phases might weave a continuity that makes a birth moment unnecessary. Several frameworks offer different answers. The no-boundary idea, where there is no edge to time, cyclic or ekpyrotic models where the universe goes through endless phases, and quantum gravity approaches where time emerges from deeper relationships rather than being a backdrop. Observations so far keep the debate alive rather than delivering a final verdict, but they guide how we test these ideas and what kinds of signals to look for. If you've ever stood under the night sky and felt how vast everything is, you're not alone. These questions touch something personal about our place in the cosmos. They invite curiosity, humility, and a willingness to let the mystery linger just a little longer. If this exploration resonated, drop a like, subscribe, and share your thoughts in the comments. What idea about time and beginnings does it bring to your mind? Your perspective matters here, and it helps shape what we bring you next. In the next video, we'll dive into how researchers might test these bold ideas in practice. What experiments or observations could distinguish a timeless cosmology from one with a beginning, and how discussions with physicists working on loop quantum gravity, no-boundary cosmology, and related ideas are evolving. We'll peel back the evidence and the reasoning that could push us closer to an answer. Until then, keep looking up and keep wondering.